In the previous video, we looked at the functional derivative, and we surmised that if we set the functional derivative equal to 0, similar to the way we do in differential calculus, that we could get the stationary function. And indeed, that is the case. But I want to take a closer look at the derivation that we did there and kind of fill in some of the gaps and address some of the nuances in a more detailed and complete way. So this is a complete derivation of what's known as the Euler equation for the particular functional that we're considering now. And it closely parallels actually the original derivation by Euler and Lagrange back in the middle 1700s. In the next video, we'll derive the Euler equation using variational notation. So in fact, we'll have 3 derivations of the Euler equation. We're starting by looking at variational calculus from the point of view of the differential calculus that we already know. So it ends up seeming a little cumbersome translating back and forth, but as we get comfortable with the variational notation, variational terminology, and methods, toss aside that differential calculus approach and focus just on the variational calculus. But in this derivation, we're going to be using the differential calculus. And so again, it will seem a little bit more cumbersome and tedious, but it'll help us to see the connections between the differential and the variational calculus. So we're going to take epsilon here as the independent variable as we go from one function to another. So remember, we're looking for u of x. We have this u hat of x, which is close by. So as we move from one to the other, the epsilon will be our independent variable. And so we're looking for that u of x for which I, the functional of u of x, has a stationary function such that the variation of the functional goes to 0. So the variation of I is 0, and remember the variation of I is di d epsilon when epsilon is evaluated at 0 times epsilon. So we've already evaluated that in the functional derivative in the previous video and set that equal to 0, and that gives us the Euler equation. But let's start from scratch, do this from the very beginning, and again fill in some of those additional details and nuances as we go. So once again, we're looking for the stationary function of our functional rather than the stationary point of a function, but you'll see a lot of similarities and analogies. We can take the derivative inside the integral because the limits of integration x0 and x1 are just constants. They don't change with epsilon. They don't change as we move from one stationary function to another. So we can say that the dd epsilon of the integral is the same as the integral of dd epsilon. So then inside we have df, d epsilon f being our integrand. Now if we look at x, u, and u prime as being our independent variables at this stage, then taking df, d epsilon will give us 3 terms, one for each of those. So we'll have partial f partial x times dx d epsilon plus partial f partial u times du d epsilon and partial f partial u prime times du prime d epsilon. Now x here really is our independent variable, and so it doesn't change as we move from one function to another signified by the epsilon. So dx d epsilon actually vanishes, and so this term is gone. So then df d epsilon is equal to these 2 terms. Now you'll notice we have this du d epsilon here and du prime d epsilon. So let's go back to our u and how it's related to u hat. Remember, u is u hat minus epsilon times eta. Now remember, these epsilons and these etas, these are kind of this translation back and forth between differential and variational calculus. When we get to the variational formulation in the next video, we won't have any need for these epsilons and etas, but for now we're doing this translation back and forth. So if u is u hat minus epsilon eta, then du d epsilon is just minus eta. And du prime d epsilon, if you take the derivative of this, will just be minus eta prime. All right, so now that goes in for du d epsilon, and this goes in for du prime d epsilon. So if you do that, put it back inside the integral then, we have the integral from x0 to x1 of partial f partial u, that's from right here, times eta, that's the du d epsilon, plus partial f partial u prime, that's this partial f partial u prime here, and then the du prime d epsilon, well, that's minus eta prime. So minus eta prime there. Now what we want to do is write this as an integral of something that doesn't involve any epsilons or etas. So I want to be able to factor this eta out of the rest of the integrand and bring it over here. So to do that, I need to get the derivative off of this eta prime. Now we saw how to do this in the previous video, but we'll go through all those same details again here using integration by parts. So this first term doesn't change, but let's look at the second term using integration by parts. So here is that second term again. So remember here, we're integrating p times dq. The dq is the part of the integrand from which we want to remove the derivative, and then the p is the rest of that integrand. So in this case, we want to get the derivative off of the eta. So eta prime dx, that's dq. And then the rest of the integrand, which is the partial f partial u prime, well, that's the p, partial f partial u prime. Okay, so then we do the integration by parts. We get the terms evaluated at the endpoints, x0 and x1. That's p times q. And then we have minus the integral of q times dp. So the q here is eta, and the dp is ddx of partial f partial u prime times dx. Now eta, remember, at the two endpoints is 0, because we know the value of u at the endpoint. So if eta is 0 at x0 and x1, then this term evaluated at the endpoints vanishes, and we just have this term left to replace this one in the integral on the previous slide. So the partial f partial u times eta, that's that first term that we didn't do anything with, and then here we have minus ddx of partial f partial u prime times eta, and then that's this term that came from the integration by parts. Now this is where the fundamental lemma of the calculus of variations comes in. So what we have is we have the integral of the product of two things. The first is in square brackets, and the second is eta. Eta is just a function, and it's completely arbitrary. It's the difference between the u and the u hat functions. So the idea is as follows. We have a definite integral of the product of two things. One of those two things is completely arbitrary. Let's think about definite integrals and how that definite integral could be 0. So say we had a situation like this. So here's x, x0, and x1. We could have a situation where the positive portion and the negative portion, those two areas, exactly compensate, and therefore it's 0. They cancel each other out, and the definite integral from x0 to x1 is 0. That's one possibility. The other possibility for a definite integral to be 0 is if the integrand itself is 0 all the way across. So you're just integrating 0, and of course the area under that curve is 0. The first case, this one, can only happen under very special circumstances. And in fact, again, here we have this integral of the product of these two things where eta is arbitrary. And so in general, for most etas, this of course is not going to be true. So we can't rely on that reason for the definite integral to be 0. So the only other reason why we could get 0 is if this second possibility is the case. And so that's what happens here. And that's the fundamental lemma of the calculus of variations. The definite integral, the product of these two things, where one of them is arbitrary, can only be equal to 0 if the piece that's not arbitrary is equal to 0 all the way across the domain. So this, the piece in square brackets then, setting that equal to 0, gives us our Euler equation. So the solution of the Euler equation, the u of x that satisfies this Euler equation, is the one that results in the stationary function for this particular functional, where the integrand is a function of x, the independent variable u, the dependent variable, and its first derivative u prime. So this is the famous equation. It's known as the Euler equation. It's also called the Euler-Lagrange equation. I will reserve calling it the Euler-Lagrange equation for cases where we're dealing with dynamics, Hamilton's principle, and so on. And for the general case that we're looking at here, well, I'll call it the Euler equation, and that's fairly typical. The key here is this is a necessary but not sufficient condition for an extremum in the functional I. This is perfectly 100% analogous to the differential case. So you have a function, u of x, and you find its maximums and minimums. So you take the derivative, set it equal to 0. That gives you locations that are candidates for being minimums and maximums, but they could also be saddle points. It could be a situation where you have a 0 derivative, but it's not a minimum or a maximum. So in order to check whether it's a minimum or a maximum, or in fact just a stationary point, you have to check the second derivative. Here it's very similar. We'll talk more about that in a moment. But in any case, for the same reason as in the differential case, Euler's equation is just a necessary but not sufficient condition for an extremum. So the solution u of x is a stationary function. It may also be a maximum or a minimum, but I don't know that without doing some additional work. So as we hypothesized in the previous video, setting the functional derivative equal to 0 does indeed give us the Euler equation 2.9 that we have here. Now you can think of this as, and this is often the way we'll talk about it, the Euler equation is an equivalent differential form of the variational form of the functional. So we can go back and forth between the variational form and the form of this definite integral and the equivalent differential form, as you'll see. One of the great advantages of the Euler equation is it's invariant in the sense that it does not change, it's not altered in any way by altering the curvilinear coordinate system. So you can do this in Cartesian, you can do this in polar coordinates, spherical coordinates, and the Euler equation remains precisely the same. This is different from a vector equation. Newton's second law, for example, F equals ma is a vector equation. F and a are both vectors. And if you put it into a different coordinate system, then it changes the form of the equation. Not the physics, but it changes how the equation looks. For invariant equations, such as the Euler equation, that is not the case. So the Euler equation is the same regardless of the coordinate system that we're working in. And that has a number of advantages that we'll see later on. Now, when you look at the Euler equation, I keep saying this is a differential equation, and you do indeed see derivatives all over the place. However, it looks a little strange in the sense that partial f partial u, remember f is the integrand, u is the dependent variable. Normally we think of taking partial derivatives with respect to the independent variables. Here it's taken with respect to the dependent variable and its first derivative. And remember we said in the beginning of the derivation that we're going to look at u and u prime as if they're independent variables. Now they're not in the context of the real problem. So this looks a little strange. This is the form that we will use, and I'll use in examples, and we'll see many cases of that. But I want you to see what the equation actually looks like in a more familiar form. So if you expand that out and carry out all those differentiations, you actually get something that looks like this, quite a bit more complicated. But what you'll notice is it is a second order equation, so it has second order derivatives of u with respect to x, first order derivatives, and so forth. Then these coefficients here, then in parentheses, those are going to be variable coefficients in general on our second order ODE. Now, is this linear, nonlinear? It all depends. It depends on how f behaves with respect to u and u prime. But in any case, it's a second order, linear or nonlinear, ordinary differential equation that we will solve to get u of x. Now again, we'll use the more compact form 2.9. It's much easier to remember and it's easier to use in practice, as we'll show in an example. But this is just to show you more explicitly in a more familiar form of a differential equation what we end up getting. Now I've said that this is actually the simplest form of the Euler equation that we'll encounter, but it's also one that has widespread applications. In fact, all of the examples from chapter 1 that we looked at, optics, shape of a liquid drop, and the river crossing trajectory problem all fit within the context of this Euler equation. And there are many others as well. So it's a very powerful case. Now the key is in 2.9 is to remember that we're looking at u and u prime as if they're independent variables. We're evaluating those partial derivatives of the integrand capital F with respect to u and u prime as if they are independent variables. Again, I'll show you this in an example. Now the admissible functions, the allowable solutions, the results u of x that you can get are all going to be continuously differentiable. So in other words, the only possible solutions of a variational calculus problem are smooth functions, as you might expect. There are cases, particularly in optimization problems, where the solution is not smooth, the optimal solution is not smooth. We'll see some examples of that in chapter 10 later on, and I'll show you how to treat that in that particular case. But we will not get those discontinuous solutions from this traditional variational approach that we're discussing right now. Now finally, just a little bit of history. So this really started in the late 1600s. If you read the bit of history section at the beginning of the chapter, you'll see names like Isaac Newton and the Bernoulli brothers and Euler and Lagrange were heavily involved in the development of the calculus of variation. So these are names that we've heard of before and we're familiar with. It was the late 1600s when Isaac Newton and the Bernoulli brothers, we'll talk more about them in a later video, that really kind of came up with some of these concepts and ideas. It was very rudimentary at the time. And then later on, about a half a century later, when Euler and Lagrange independently formalized this development of the Euler equation, this derivation as you see here. And so that was in 1744 and 1755. It turns out Lagrange was 19 years old when he did this derivation, so I'm way past my prime, apparently. Now, this is not actually an advertisement for the book, although it is an excellent book. But what I wanted to show you is the reason for the covers. This is an arch of a church in Europe. And if you look at the center, you'll see patterns and shapes that are reminiscent of this era of when the calculus of variations was developed in the late 1700s. But then as you move radially out, you'll see that the shapes and patterns get increasingly more modern looking. And what I'm trying to portray in the choice of this picture is that that's really the way of calculus of variations. That it started out as this fundamental calculus that was developed to address these very specific problems. In fact, they're optimization problems. And at the time didn't seem terribly useful. But then over the years, in fact, over the decades and centuries, the uses expanded and grew to the point now where it's just ubiquitous across many, many different areas of science and engineering.